Good morning everyone. Last time we have learned what is the superposition principle for waves. Let's revise it quickly. What we have learned is that if there are two independent waves, on some medium, maybe a string, maybe in air, anything, right? So when there are two independent waves, the particle will get displacement that is equal to the sum of individual displacements due to each wave, right? That is, if the first wave is going to give it a displacement y1, second wave is going to give it a displacement y2 independently, then if both waves are there on the same string or on the same medium, then when both the waves arrive at that point, it will get a total displacement y equal to y1 plus y2. Okay, yes, I am waiting for things to get. We have learned last time that when there are two independent waves in the same medium and they are affecting one particular point, then what happens is that particular particle or point will get displacement which is equal to the sum of the individual displacement due to each wave. That is, the first wave is giving it a displacement y1, second one would give it a displacement y2, then the total displacement would be y2 y1 plus y. Correct? So this is clear, right? This is the superposition principle that we have learned the last time. Okay? Right? Clear? Fine. Let's continue with that. Okay. Now we are going to use this superposition principle. We are going to use the superposition principle to understand how a wave gets reflected when it reaches the other end. Okay. So I know at the start some of you had this question. What would happen when the wave reaches that other end and how will it get reflected and all that? Okay, so it's time to answer all that now. Okay. So, first of all, we will study reflection of wave from, actually reflection of string wave from a rigid end point, okay, or a rigid boundary. Okay. What does this mean? Rigid, first of all, is something that is fixed. It can't move in any way, it can't change in any manner. Right? That is what is rigid or fixed. So, for example, there is a wall. Let's say there is a wall, and to the wall we have fixed a nail. Okay, right? If you fix a nail to the wall and then you would attach a string to that. Okay, you tie a string to it, and now let's say this is the string and this is in your hand. Okay, understood what I've drawn so far, right? Okay, so we have that the string is fixed to the string is fixed to the wall, right, with a nail. So obviously this point is a fixed point. Yes or no? This point is a fixed point. Clear? Okay, so now we will see what will happen as the wave reaches there. But before we actually go to that point, I want you to answer a simple question that I am going to ask you. Let's say that we want to generate, suppose we want to generate this kind of wave pulse from this source, okay, which is in your hand. Remember, the point S is the source that is in your hand. So in this condition, what should we do? That is basically I am asking you which kind of forces should we apply on the source point S. That is, should we apply force right side, left side? What should we do? Which kind of force should we apply? What direction of force should we apply so that we can generate this kind of wave pulse? Come on, can you answer that first of all? Which kind of wave pulse? If you want to generate this kind of wave pulse, then what kind of force should we apply? Okay, Joy, are you sure about that? There's more to it. Come on everyone, I am expecting answers from all of you. Okay, we have got some answers. No. I asked you a question that if you want to generate this kind of wave pulse, what should you do to the point X? Think about it. What should you do to the point S? You should move it, correct or not? How should you move it? How should you move it to generate this kind of wave pulse? Forget about this part. We are not even talking about all this. We are just focusing on what we have learned earlier. Come on. I am asking you what kind of motion should happen over there along the y-axis. Okay, but can you be more specific? Along the y-axis can be like this also. If it goes down and then goes up, will it create this kind of wave pulse? Ask yourself this. If source goes down and then goes up, will it create this shape of wave pulse? No, you are not being able to answer that question specifically. Never mind, I will answer it myself. Yes. Okay, see, bad things happen when you don't answer questions. Okay? Well, hopefully you can see on the board. So I was saying that you hear me, can you see me clearly? The board is clear, everything is fine. Okay. Right. So I was asking you about this point, that when we want to generate a wave pulse of this particular shape, okay, which is upwards from the mean position, then it is necessary first of all to apply force upward on the source, and then after some time we also need to bring that source back. So first we have to apply force upwards and then we have to apply force downwards. Is this clear? Is this clear? Not clear? I'm surprised. What's not clear? If you take this source, you have to move it up and then you have to move it down. Only then you are going to get this kind of shape. Right? Okay? No problem then. So, what that means is is when you apply force upwards and then downwards, you get this kind of wave pulse traveling on this string. Now we will see what happens as this wave pulse reaches here. Okay, we will see what happens when that wave pulse reaches that fixed point. Okay. So, first of all, let's draw just one case where the wave pulse just reaches that fixed point, like this. Okay? Right? Just reaches that fixed point. Okay. Now, what happens here is that beyond this time, right? So far, let's say the wave pulse has traveled all the way from here to here. Okay. Now, the moment it reaches here, what happens is that when it tries to travel forward further, this point always remains fixed. Correct? This point will always remain fixed. But if you would consider it, why would it remain fixed? Why would it remain fixed? Can you tell me? Why would this point remain fixed? Don't say that it is attached by a nail. Okay, that's a very childish, very kiddish answer. I don't want that. Use some physics explanation. Why does this point remain fixed? No answer? Come on everyone, give it a try. Okay. Let me answer it again. It's that if you think of the molecules of that string, let's say these are some molecules. Okay, and this is that last point. This is that last point of the string which is attached to the nail. Okay. Now why would this remain fixed? It's that this particle will try to pull it up, right? That's what we expect. See, if it was at any other point, let's say it was over here, then if there is one point here, then we realize that the other point which is slightly higher is definitely going to pull, right? This point will definitely pull this up like this. Yes or no? So that's why the wave will travel and then this point will also rise. Clear or not clear? This is what would happen over here, right? Each point will pull the next point up. Clear? Each point pulls the next point up. Okay. But if you try to think about it here, so this second last particle will pull this up. Very good. Second last particle will pull this up. Okay? Right? But it still won't move. Why? Because the nail is fixed in the wall. So whenever a force is applied like this from the particle of the string, there will be an opposite force. There will be an opposite force applied by the molecules of the wall. You understand that? That's why this would remain fixed. It's basically whatever force the particles of string apply, the same force but in opposite direction, the molecules of the wall will apply and everything will get cancelled. So that's why this last particle on the string will always remain fixed. Is that clear? What I said is clear or not clear? Okay, very good. So now what we are having is as follows: that when the wave would arrive, okay, on any typical point, maybe this one. So first of all, the other particles will pull it up, Okay, not exactly vertical but at an angle, but horizontal components are always going to get cancelled. So don't worry about horizontal components. So this will get pulled up by which particle? The one over here, right? But then later on, when it goes up and the wave has already traveled forward, so now this particle has risen up. Okay, so now the wave pulse has traveled little bit forward. I hope you can see what I've drawn. It was here, it has moved little bit forward. So now the particle that we are talking about has already gone up. Now what will happen is that the particle over here will pull it down. So basically, everything gets this treatment. Yes or no? Everything gets this treatment. Every particle will first be pulled up and then it will be pulled down. Yes or no? Is that clear? Every particle on the string will first be pulled up, so it will go up. And then it will also be pulled down, so it will come back to mean position, and that's how the wave pulse will travel forward. Okay? So if you keep that idea in mind, for this last particle, then what will string do? That is, what will other particles of string do to that particle? Okay, other particles of string, they first pull it up and they pull it down later. Okay, first pull it up, then pull it down. So what should wall do? What should particles of the wall do to this point? I repeat, what should particles of the wall do to this point so that this remain fixed? They should do opposite. First the particles of the wall will push it down and then they will push it up. Is this clear? The wall pushes this point over here like this. First down and then up. Is it clear or not clear? Opposite. Basically, it's going to be the opposite. Right? So, what happens is when the string tries to pull this last point up, the wall will pull it down. When the string tries to pull the last point down, the wall will pull it up. So, ultimately, all the forces will get cancelled. But there is a side effect of doing this. What's that? Think about it. You take any point, okay, let's say in your hand, no problem. Let's consider it with the hand. Suppose instead of applying force upwards first and downwards, then if you would reverse this, instead of applying force upward first and downward, then if you reverse this, what do you expect? Will the wave pulse will still be like this, or will there be some change? What do you expect? Will the wave pulse will still be like this, or will there be some change? What change? The same change isn't enough. What change will happen? Raj, can you please be more specific? Mirror image, but in which way? It will move along negative y-axis. Are you sure, Ankita? How can the wave move on y-axis? Okay, so obviously if you reverse the forces, the wave pulse shape will also be reversed. Do you understand? If you do it like that, you will get this kind of wave pulse. Clear or not clear? You get this kind of wave pulse. Clear or not clear? I said that to keep the point fixed, the wall must always apply opposite force on the last point of the string. Remember, we are talking about last point of the string. I said that to keep that last point fixed, it is necessary that the wall always applies opposite force of what the string applies. So, what is basically happening is that now this wave pulse arrived here, alright, no problem. But as it arrives, there is something else happening from the wall side of things. What's that? The wall is pushing that point down and then once again pushing it up. So that would mean that from the wall, from the fixed point on the wall, there will be a new wave pulse generated like this. Do you realize that there will be a new wave pulse generated like this? Why so? Because wall has pushed that last point down and then up like that. Clear or not clear? Again, to keep the point fixed, the wall must apply opposite forces always compared to what string applies. So because of that, it's just like you take a string in your hand and you push it down and then up. Okay, so do you realize that it would make this kind of wave pulse? Okay, this shape of wave pulse, like I explained here. Okay, but now this wave pulse started from this point. The wave pulse started from this point, the fixed point. So now this wave pulse will obviously not travel in the wall, it will travel back on the string. Right? So this is what is reflection of wave. What do I mean? Incident wave was like this. Okay, these are two separate diagrams about the same string. Okay, don't say why are there two strings? There are not two strings. There is only one string. I am drawing it separate. So if you send a wave pulse like this towards the right side and this point is immovable or fixed, then what will happen when the wave pulse will reach there? It will bounce back. It will reflect. See, this is reflection. It will hit the wall, it will come back. Okay, but when it comes back, its shape will get inverted. Did you understand what I have drawn? This is the reflected wave, and this diagram upper one is called incident wave. Clear or not clear? Okay, so if the incident wave is upward like this, when the wave gets reflected by this fixed point, when the wave gets reflected by the fixed point, it will get inverted. Okay, again, why does it get inverted? It is necessary to get inverted because of this point being fixed. Reason: to keep the point fixed, the wall should apply opposite forces. Obviously, when you reverse the direction of forces, what it does is creates a wave that is inverted. So this one was created by pushing it up and then down, but here the wall is pushing it down first and then up. So because of that, this becomes a new source, but this source is of the reflected wave. Is that clear? The last point here on the string becomes the source of reflected wave. Now the reflected wave travels left side, but because the forces have been reversed compared to this, the wave pulse shape is also inverted. Did you understand? Okay. How is wall reflecting? Idea is simple. What is meaning of reflecting? Have a look. This is reflecting. Okay? What I mean to say is that whenever something moves towards a surface, it hits there, forces are applied. Clear or not? It hits there, forces are applied, and it bounces back. That is what is called reflection. Did you get that first of all? Yes or no? Okay. So what did happen here? when the wave was arrived here, the wall started applying force. The wall started applying force. So that's why the energy that was traveling towards the wall, remember, wave is transfer of energy. Okay, from one point to another point. Wave is not an object. So the energy that was being transferred towards the wall, when it reaches that last particle, the wall applies opposing forces and throws it back. Did you understand? Did you understand or not? So that's how the wall reflects the wave. Okay? That's how the wall reflects the wave. Okay? So, time to write the summary of this particular topic. It is that when a wave is reflected from a rigid or a fixed, that is immovable, remember, endpoint or boundary. When a wave is reflected from a rigid or a fixed endpoint or boundary, the wave pattern of reflected wave is inverted compared to incident wave. Okay, so in diagrams you can actually draw these two diagrams. I have drawn it very nicely. I don't want to draw it again. Everyone, draw these two diagrams. Okay, remember this only happens if this point is immovable or fixed. Alright, draw these diagrams. That will help you understand what we are writing here. Of course, the reflected wave comes back. There is no surprise about that. Right? These arrows are not the main thing. This is expected. That's what is called reflection. Correct? Reflection means coming back in the opposite direction. What is important is that the wave pulse got inverted. Is that clear? Okay? So make sure you draw these diagrams. Done? Everyone? Okay. Next time we will see another way for explaining what is really going on between these two. That is, what happens after the incident wave touches the wall. Okay? What happens after the incident wave touches the wall? Alright? Okay, and between this, that is while reflection is going on. I'm saying while reflection is going on, what happens at that time? Right? That's what we will draw, and we will also write one or two equations for the same thing. Okay? So with that, we're going to end today's